So we are in the middle of a discussion of a very important chapter. A short question is there in JEE Advanced as well as JEE Mains as well as any state board examination, that is from the chapter of solutions. Okay, so I hope you have attended all the lectures. We have almost completed the lecture. So today I am just going to talk about a Henry's law and I am going to solve some advanced level questions. Okay, so that are often asked in JEE and there are some previous questions also incorporated with it. Okay, so I hope like we have almost now completed more than 1 month together. So I hope you are comfortable with the platform. Hope you have understood all the things that are there on the platform. In case you have any technical issues facing, you are not able to view any of the lectures or is like any problem exists, so just write to us so that we can correct those things and the process becomes smooth for you. So let's start the lecture. So today I was basically I want to discuss a few points on Henry's law, what exactly is Henry's law and how do the Henry's law affect the solubility of gases in liquid solutions. Okay, so coming to the first point, that today we wanted to discuss the solubility of a gas in a liquid. Okay, so let us take an example to understand that. Suppose we are having a liquid. Okay, so we are having any container, okay, which is having a liquid. Okay, so we are having a container which is filled with a liquid. Okay, so suppose this is our solvent. Okay, now we are dissolving a gas. Okay, so there are gas molecules. So we are dissolving the gas in the liquid, okay, or in the solvent that is contained in the container. Okay, so the first point which I will describe over here is the solubility of this gas in the solvent. So basically solubility of a gas in a solvent is defined as the amount of gas, okay, in centimeter cube which will dissolve in 1 centimeter cube of the liquid to form a saturated solution at a particular temperature and pressure is called as the solubility of a gas in liquid. Okay, so you take a container, it is having a solvent, you just take some gases, okay, the gas will get dissolved, the gas will go into the liquid. Okay, so the amount of gas, okay, in centimeter cube which is getting dissolved in a particular solvent, okay, in a particular 1 centimeter cube of a solvent at a particular temperature and pressure is called as the solubility of a gas. Okay, I hope this point is clear to everyone. Okay, so now let me just ask you 2 or 3 very basic things. Okay, so we want to dissolve this gas in the solvent. Okay, so what factors will control the solubility of this gas in the solvent? Okay, the first is the pressure. If I keep on increasing the pressure on the gas, okay, if I keep on increasing the pressure on the gas can easily go and sit inside the liquid solvent. So I will say that at higher pressure, the gases will be more soluble in the solvent as compared to that at the lower pressure. So if you increase the pressure, the gas can easily dissolve in the solvent. Okay, hope this is clear to you. Now the second point is whether this is an exothermic or an endothermic process. Now we know that if you consider a gas, we know that gas will have some kinetic energy. Okay, gas molecule will obviously keep on moving here and there. Okay, so it has a random motion. Okay, so initially the gas is having a very high energy because it is having random motion moving here and there because of its thermal energy which is directly proportional to the temperature. Now when you dissolve that gas in liquid, so what will happen when you take that gas in the liquid, its motion would be restricted. Now the gas cannot move freely because there is a viscous medium which is stopping it to move. The liquid is basically offering a drag due to which the gas cannot move. So gas initially was free to move. Now when it has been taken in the liquid, okay, the gas will become sluggish, it will become slow, it will not be able to move easily. So whatever excess energy it had, initially gas had some energy, when you have taken it into the liquid, the gas must have lost some energy. Okay, then only the gas molecule is becoming sluggish. So that energy goes out, okay, and it appears as the heat of dissolution. So whenever we are dissolving a gas in a liquid, so heat is always released out and it is an exothermic process. Okay, because you know that gas initially was at a high kinetic energy, it was free to move in the medium, when you took it in the liquid medium or the solvent medium, its motion got restricted. Okay, the kinetic energy of the molecule decreased. So initially it had some kinetic energy, now the kinetic energy decreased. So the excess energy which it had in the gaseous medium, it will lose out in the form of heat. So that is also called as enthalpy of dissolution. So when a gas dissolves in a solvent, it always releases energy and it is an exothermic process. Okay. So when you are dissolving a gas, okay, in a solvent, so we are forming a saturated solution, okay, and we will say that heat is always released out. So you can see that this is a exothermic process. Okay. Now if this is an exothermic process, according to Lee-Chatterjee principle, if we decrease the temperature, okay, whenever we decrease the temperature for an exothermic reaction, the reaction would come to the forward direction. So for this process, if you are decreasing the temperature, more and more gas would dissolve in the solvent. Okay, this is also very logical. If you decrease the temperature, the kinetic energy of the gas molecule would decrease and it can easily sit inside the liquid. Okay, so we'll say that more and more amount of gas would be dissolved in the liquid solvent. Now if you increase the temperature, okay, when we increase the temperature, we'll say that the gas molecule which is sitting inside the solvent will have more kinetic energy. So when the kinetic energy increases, it can easily escape out and come out of the solution. So the amount of gas dissolved in that case would be less. So when you increase the temperature, okay, the kinetic energy of the gas molecule increases, due to which the molecules which are sitting inside the solvent or in the solution would have increased kinetic energy and they can come out easily from the solution. So the amount of gas that would dissolve in that solvent would decrease. Okay. So also this is an exothermic reaction. Now we know that according to Lee-Chatterjee principle, if we increase the temperature for an exothermic reaction, the backward reaction is favored. So if the backward reaction is favored, it means that the gas will come out from the solution and hence the solubility of the gas would decrease. Okay. Hope this is clear to everyone. Okay, so if I consider the factors that affect the solubility, the first one is the nature of the gas. Okay, now we know that some of the gases would be highly soluble in water and some of the gases would be very less soluble in the water. Okay, so all those gases, all acidic or basic gases, okay, we know that acidic gases like CO2, NO2, okay, say SO3, they will be highly soluble in water because they can enter into water and react with it and form an acid. So all acidic and basic gases like ammonia, if you keep a container containing a water and if you add ammonia to it, ammonia will be in the dissolved form and it will form ammonium hydroxide in the solution. So all acidic gases, okay, like NO2, SO2, even vapors of HCl, and basic gases, okay, basic gases like ammonia would be highly soluble, okay, would be highly soluble in water. But if you consider say O2, N2, hydrogen, helium, so they are soluble in water but to a very small extent. Okay. Now how do we know that water can dissolve oxygen? So if you look at river, lake, sea, okay, so they basically contain water. Now they support aquatic lives. So there are so many aquatic animals living inside them. So all those aquatic animals would need oxygen for their respiration process. Okay. So obviously they have that O2 present inside. That's why they are surviving inside the water. So basically the O2 from the atmosphere would dissolve in the river water, lake water, the sea water, and it is available for the aquatic animals. So O2 is soluble in water but to a very smaller extent as compared to these gases which are acidic and basic, because they can easily dissolve and form a acid or base in the solution. Okay. So the next is the effect of temperature. Now we know that with increase in temperature, okay, with increase in temperature, solubility of gas in liquid decreases. Okay. So we can say that whenever you have taken a gas and you are dissolving it in a solvent, so there would be an equilibrium established and we would get a saturated solution. This process is an exothermic process. So if you increase the temperature, backward reaction would be favored, the gas would be evolved out. Also you can say that with the increase in temperature, the kinetic energy of the gas molecule increases, so their tendency to escape from the solution also increases because they have more kinetic energy, so they can easily come out of the surface of the liquid or the solvent in which it is contained. So the solubility of that gas on increasing the temperature will obviously decrease. Okay. Next is the effect of pressure. Now I have already told you, if you increase the pressure, the gas molecule will easily go inside the liquid, penetrating the surface of the liquid or the solvent. So with increase in pressure, the gas molecule can easily go inside the liquid solvent. So we say that with increase in pressure, okay, with increase in pressure, solubility of gas in liquid increases. Okay, hope this is clear to everyone. Okay, so these are the three factors on which the solubility of a gas in a liquid depends. Okay, first is the nature of the gas. All the gases which are acidic or basic are more soluble in water as compared to the gases which are inert or gases which do not react with water, like O2, N2, H2, helium. Okay, with increase in temperature, the solubility of gas will always decrease, and with increase in pressure, the solubility of gas in liquid will always increase. So the up arrow over here shows increase, and the down arrow which I am showing, okay, it indicates that the solubility is decreasing. Okay, hope this is clear to you. You can take a snapshot of this. Okay, so I am just rushing through this because I want to enter into the problem solving. Okay, next comes is the Henry's law. So basically Henry's law is a quantitative analysis of these gases dissolving in a particular solvent. Okay, so Henry's law basically says that the mass of the dissolved gas in a particular solvent or in a particular liquid is proportional to its partial pressure above the liquid. Okay, so if m is the mass of gas, okay, that is dissolving per unit volume of solvent, okay, per unit volume of solvent. So we'll say that the mass of this gas dissolved will be proportional to the partial pressure or the pressure above the liquid. Okay, partial pressure of the gas above the liquid. More is the partial pressure, okay, more easily can the gas molecule penetrate through the surface into the liquid, more will be its solubility. So if you remove the proportional sign, this will come as K into P. Okay, hope this is clear to you. Now if you look at a graph, so this is basically solubility versus pressure graph. Okay, now you can clearly see that at any given pressure, the solubility of O2 will be more. Okay, at this particular pressure, the solubility of O2 is more than that of N2 than that of, okay, helium. So we'll say that solubility of O2 is more than that of solubility of N2, solubility of N2 is more than that of solubility of helium. Okay, hope this is clear to you. So if we rewrite this equation, okay, if we divide with molar masses and we just rework on the expression, so this would come out to be, okay, the expression would come out something like this. Okay, so the expression would come something like this: P is equals to Kh into mole fraction of the gas, where Kh is called as the Henry's constant. Okay, so we'll say that the amount of gas or the amount fraction of the gas that is getting dissolved in a particular solvent is proportional to the partial pressure of the gas. Okay, now when you remove the proportional sign, you get a constant. Okay, so P is equals to Kh into X gas, where X gas is the mole fraction of the gas. Okay, so Kh here is called as Henry's constant. Okay, sorry, this is called as Henry's constant. Okay, hope this is clear to you. So this is the expression from Henry's constant. Okay, so if you look at the graph, so this is the graph of the Henry's law. So now we know that Henry's law say that partial pressure is equal to, partial pressure of the gas is equal to Henry's constant into mole fraction of that particular gas. Okay, where Kh is the Henry's constant. Okay, so if you look at this, solubility gradually increases with increase in the partial pressure. So if you keep on increasing the partial pressure above the liquid, the gas can easily penetrate through the surface and enter into the liquid solution. So we'll say that more amount of gas would be soluble in a given solvent. Okay, so this is the expression from Henry's law. It resembles Raoult's law. Okay, so Raoult's law was basically P was equal to P naught into mole fraction. Okay, so we are saying that if we are having like any solution, okay, the pressure over the solution will always be proportional to the mole fraction of the solvent. Okay, so partial pressure was always proportional to the mole fraction of the solvent. So if you remove the proportional sign, you will get P is equals to P naught into mole fraction of solvent. So you can see that this is mole fraction of gas, this is mole fraction of solvent, this is partial pressure above the solution, this is partial pressure above the solution. So this is a constant Kh, okay, which is called as Henry's constant, and the constant in the Raoult's law was P naught. Okay. So Henry's law states that the pressure over the solution in which the gas is dissolved is equal to the amount fraction of the gas multiplied by the Henry's constant. Okay, so this is our expression. Okay, hope this is clear to you. So how we arrived at this formula is not that important. So we basically converted the mass, which is proportional to pressure. Mass was equal to K into P. Okay, so we divided with molar mass, we converted into moles, then we again divided with total moles, and we got this formula. So you don't need to know how you got this formula. So if you are just comfortable with the formula, then it is a very easy case. Okay, so now let us look at the significance of Kh or the Henry's constant. Okay, significance of the Henry's constant. Now, if a gas is more soluble, at a given pressure, okay, so pressure is a constant at a given pressure we are saying. So if the solubility of the gas is more at a given pressure, it means that the mole fraction of gas in the liquid would be more. Okay, so if the mole fraction is more, okay, at a given pressure, then the value of Kh would be low. Basically Kh is P upon X gas. If we fix the pressure, okay, if at particular pressure the gas is dissolving more, so the mole fraction of gas in the liquid would be more, hence we will say that smaller would be the value of Kh. So we say that smaller is the value of Kh, okay, smaller is the value of Kh, more would be the solubility. Okay, hope this is clear to you. So we are saying that at any given pressure, okay, we know that at any given pressure, if the gas has dissolved in the solvent to a very higher extent, it means that the mole fraction of gas would be very high. So Kh I would write at P upon X. Okay, now because X is very high, so the value of Kh would be low. So smaller is the value of the Henry's constant, more would be the solubility of the gas in that solvent. Okay, hope this is clear to you. Okay, so this basically tells us, Henry's law is basically speaking about the amount of gas dissolved in a particular solution, okay, or in a particular solvent. Okay, so let us look at one question to understand. So this says that the Henry's law constant for solubility of N2 gas in water is 1 into 10 raised to the power 5. So we know that the value of Henry's constant is 10 raised to the power 5 atm. Okay, the mole fraction of N2 in air is 0.8. Okay, so the mole fraction of N2 in air is 0.8. So rest 0.2 mole fraction which is left would be O2. Okay, because N2 and O2 are the main constituents of air. Okay, 79% is N2 and close to 20% is O2. Rest is helium, okay, argon and all those gases. So we know the mole fraction of N2 as 0.8. The total pressure, okay, the number of moles of N2 from air dissolved in 10 moles of water at 298 Kelvin and 5 atm pressure. So we know that the total pressure is also 5 atm. Okay, so the partial pressure of N2 would be the mole fraction of N2 into the total pressure. Okay, so partial pressure of N2 would be equal to mole fraction of N2 into total pressure. So the partial pressure of N2 would be 0.8 into 5, which is 4 atm. Okay, so this question basically says that we are having 10 moles of water. Okay, we are having 10 moles of water and the temperature here is 298 Kelvin. Okay, and the total pressure in the atmosphere was 5 atm. Now the mole fraction of N2 was 0.8. So the partial pressure of N2 over the liquid solution would be, or over the liquid over the water would be 4 atm. Okay, so some N2 would also go and dissolve in the water. So this is basically asking the number of moles of N2 that would dissolve from air in 10 moles of water would be. Okay, so we know this. So we'll basically apply the Henry's law. So we know that Henry's law is partial pressure of N2 would be equal to mole fraction of N2, okay, divided by, mole fraction of N2 into the Henry's constant. So when we know the, we know the partial pressure of N2, which is 4 over here. Okay, the Henry's law constant is 10 raised to power 5 into mole fraction of N2. So the mole fraction of N2 I can write it as 4 into 10 raised to power minus 5. Okay, now the mole fraction of N2 in the liquid would be number of moles of N2 upon number of moles of N2 plus number of moles of water. Okay, so this will be the mole fraction of N2 in the liquid solution. Okay, so this is equal to 4 into 10 raised to minus 5. Now you can clearly see that this value is very small. Okay, it means that the moles of N2 would also be very small. Also you can say that because the value of KH was very large, KH was 10 raised to 5. So we know that the amount of N2 that would be dissolving in water would be very less. So we know that the number of moles of water was 10. Okay, number of moles of N2 we have to calculate. So I can approximately say that this will be equal to 10. Okay, because the amount of N2 dissolved in water is very less because the value of KH is very high. So I will write number of moles of N2 dissolved would be 10 raised to minus 5 into 4 into 10. So number of moles of N2 dissolved would be 4 into 10 raised to minus 4. Okay, so this is the right answer. Okay, so this is the basic application of Henry's law. Henry's law states that the partial pressure above the solution, okay, in which a gas is dissolved is always proportional to the mole fraction of that gas in a particular solvent, just like the Raoult's law. ठीक है, एक कंटेनर है, कंटेनर में पानी है, बाहर से गैस डिसॉल्व कर रहा है, तो बाहर जो पार्शियल प्रेशर लग रहा होगा that will always be proportional to the number of moles of the gas present in the solution. Okay, so the partial pressure above the solution, okay, in which a gas is dissolved is proportional to the mole fraction of N2 or mole fraction of the gas in the solution. So when you remove the proportional sign, constant aa jayega, which is KH. Okay, hope this is clear to you. Okay, you can look at the steps. Now you have found out that number of moles of N2 dissolved is 4 into 10 raised to minus 4. Okay, so approximation is also right because we have neglected 10 plus N2 as 10. So if number of moles of N2 is 4 into 10 raised to minus 4, 10 plus 4 into 10 raised to minus 4 will obviously be approximately equal to 10. So approximation holds true. Okay, so I have directly used the approximation because KH was very large. It means that the number of moles of N2 dissolved in water would be very small. So 10 plus that would be very small. Okay, because also you can see that this value is small. So if you consider denominator, numerator by denominator, okay, so obviously denominator would be having a very large value. So N2 was, and this numerator should be having a very small value. So that's why we have neglected and said that 10 plus number of moles of N2 is approximately 10. Okay, so this is what Henry's laws say. If you are having a container, you are dissolving a gas. So the pressure above the solution when a gas is dissolved in a solvent will always be proportional to the amount of or the mole fraction of the gas that is dissolved. Okay, so the pressure, partial pressure above the solution is proportional to the number of moles of the gas dissolved in the solution, and when you remove the proportional sign you get a constant which is Henry's constant KH. Okay, Hope this is clear to you. Okay, so if you look at the application of Henry's law, okay, so one common application is, everyone might have like seen the cold drink bottles, okay, Pepsi, Coca-Cola, Thumbs Up, okay, any carbonated drink. So we know that in the carbonated drinks, CO2 is dissolved. Okay, so when you just open the can, so what you get? You see that CO2 is bubbling out. Okay, so this is one application of Henry's law. So what we have done, we have airtight that bottle so that pressure is more, so that CO2 remains dissolved in the solution. So we say that to increase the solubility of carbon dioxide in soft drinks or soda, the bottle is sealed under high pressure. So we seal the bottle under high pressure so that all the CO2 is dissolved inside the inside the solution, whatever soft drink you are having. When you release the cap, or when you open the can, you can see that, because just when you open it, the pressure inside the bottle, or the compressed air that was present inside, on releasing the cap would come outside. So the pressure would decrease and the CO2 will also come out. So we know that on increasing the pressure, the gas dissolves more in a liquid. So that's why we have increased the pressure in the aerated drinks or the soft drinks, so that CO2 remains dissolved in the drink. Okay. Now second very important application is, if you have seen the scuba divers or the sea divers, you must have seen that they directly go into the sea. They have a big cylinder behind from where they get the supply of O2. Okay. Now one thing that should come in your mind, suppose I have dived in a sea. Okay. So when I go to the bottom, okay, so the pressure keeps on increasing. We know that as we go, as the depth increases, the pressure increases. So as the pressure increases, the solubility of O2 in the blood would also increase, because what we are doing, we are taking O2 from the cylinder. Now that O2 is taken up by the hemoglobin in the blood and it is transported to the lungs. So when you go inside, because of the depth, the pressure increases. Now when the pressure increases, we know that more amount of gas would be dissolved in the solution, because pressure has increased. So more amount of O2 will dissolve. Now that cylinder also contains some amount of N2. So when you are going inside as a sea diver, so you are obviously inhaling O2 as well as some amount of N2. Now when you suddenly come up, on the surface, so what will happen? The pressure would automatically get lowered, because at the depth the pressure was higher, at the surface pressure would be low. So as the pressure becomes low, suddenly what will happen? All the gases that were dissolved in the blood would eventually come out. Now when it comes out, especially when N2 comes out, it creates a bubbling in the blood. And that bubbling is dangerous. It leads to cardiac arrest, it leads to growth of tumors. So suddenly what happens, if that N2 is evolving out from the blood, so there would be a bubbling in the blood, and that bubbling could lead to a disease which is known as bends. So to avoid bends, when the scuba diver is diving inside the water, you know that when you reach the bottom, the pressure would be very high. So the scuba diver would inhale, or the O2 and the N2 will get dissolved in his blood very quickly. Now as he comes on the surface, the pressure gets lowered. All those dissolved O2 and N2 should be liberated out, because the pressure has reduced. Now suddenly when N2 comes out, it creates a bend. So what happens? We also take some amount of helium. So if you see the tank that is there behind the scuba divers, so that is basically having helium. So helium, when it goes out of the blood, it goes out smoothly and does not create bends. So N2 is basically diluted with helium, so that there is no bend formation. Because if you directly dive, say without any mask or without any support of oxygen, and you can say you can stay alive in water for say 5 minutes. So you can go and touch the bottom. When you touch the bottom, the pressure would be enormous. So the amount of O2 and N2 that you will be inhaling, that is there in the water, would be very high. So all those gases will enter into your blood. Now when you come on the surface, suddenly the pressure drops. So all the excess O2 and N2 that you have breathed in would come out. Now when it comes out, the N2 would suddenly come out with a lot of jerk and would create a bubble in the blood. Okay, so that bubbling is a disease that is known as bends. So that will basically create a bubble and it would eventually lead to a medical condition which is known as bends. So to avoid bends, okay, we take helium in the container so that less amount of N2 enters into the blood and it is eventually easily passed out from the blood. Helium passes out also easily. So that's how scuba divers work. So it is basically based on Henry's law. Henry's law says that the mass of the gas dissolved is proportional to the pressure, okay, the partial pressure. Okay, hope this is clear to you. So we also say that Raoult's law is a special case of Henry's law. Okay, so again this is a very important text. Raoult's law is a special case of Henry's law. So if you look at the graph, okay, so suppose we are plotting partial pressure with mole fraction. Okay, so the mole fraction of A is 1 over here. So mole fraction of A would be 0 over here. So the mole fraction of B is 1 over here and B would be 0 over here. Okay, suppose this is the graph of the solution shown in the black line. Okay, now we have already said that Raoult's law is applicable only for dilute solutions. Okay, so if you are considering only solvent, okay, so it will be dilute when XA is 1. When XA is 1, we will say that, or is approaching 1, we will say that very less amount of solute is there. Okay, so if it has approached 1 somewhere around here, so you can see that somewhere around here we will say that the solution is highly dilute. Okay, the mole fraction of solvent is very close to 1. That means the amount of solute present is very low. So if you draw a tangent from here, okay, so this will go and join at the origin. So this is basically the variation of this pure solvent, okay, with addition of solute that was there in your Raoult's law also. So this is basically your Raoult's line. So you can see that I have already told you this was a graph of real solution. Okay, but when the solution is highly dilute, okay, that means very less amount of solute is there. So at this point you can see that this is your Raoult's line. Now this is tangentially approaching the curve of the total pressure of the real solution. So we say that when a solution is very dilute, Raoult's law will be obeyed because the solution behaves ideally. Okay, so we'll say that at very low concentration, okay, or at a very at infinite dilution, or where the mole fraction of solvent is approaching 1, okay, the solution will be ideally dilute and it will obey the Raoult's law. So you can see that in this region it is almost a straight line. Okay, in this small region, this is the variation of the pressure is almost a straight line. So if you draw a tangent, so we will get the Raoult's line. So we will say that at this particular concentration, this real solution behaves ideally. Okay, hope this is clear to you. So the solvent follows Raoult's law under very dilute condition. Now similarly, if you look at the solute side, okay, if the solute is very small, okay, if the solute is very small, that means again the solution is dilute only, okay, because if the solute is very small, the mole fraction would be approaching 0. So this is closely approaching 0. So you can see that if you join this, so this comes out the straight line. Okay, so this is asymptotically approaching the graph. So we'll say that this is the Henry's law. So we say that a solvent component obeys Raoult's law under dilute condition, then the solute which is present inside it would be obeying the Henry's law. Okay, the solvent obeys Raoult's law in a dilute condition and the solute would obey the Henry's law. Okay, so hope this is clear. अगर थोड़ा भी दिक्कत है तो ऐसे समझो कि पहले हमारे पास क्या था, एक सॉल्वेंट था, उसमें गैस को हमने डिसॉल्व किया था. सो ऑब्वियसली गैस का जो अमाउंट डिसॉल्व था वो काफ़ी कम था. ओके, तो हम ये बोल रहे थे कि वो गैस जो है वो हेनरीज लॉ ओबे कर रहा था. ओके, अभी जो लिक्विड सॉल्वेंट है वो हमेशा राउल्ट्स लॉ को ओबे कर रहा होगा. ओके, सो होप दिस इज क्लियर टू यू. सो वी से दैट राउल्ट्स लॉ इज अ वेरी स्पेशल केस ऑफ हेनरीज लॉ. अगर सॉल्वेंट, इफ सॉल्वेंट इज following the Raoult's law, then the solute at a very small concentration range, okay, will follow the Henry's law. So if you join this line, okay, so this would be the Henry's law. Okay, so if you extrapolate when it meets over here, so it means that only solute is present, okay, only gas is present. In that case we are saying that solute is the gas and solvent is the liquid. Okay, so when you join this, so it will only be the gas. So this would correspond to the pressure of that particular gas. Okay, so Raoult's law is a special case of Henry's law. Okay, so this is all about Henry's law. So let us just start solving some question. Okay, so just look at this question. During depression or freezing point in solution, the following are in equilibrium. Now I have already told you freezing point is the temperature at which the vapor pressure of the solid solvent and the liquid solvent becomes equal. So we say that only solid solvent and the liquid solvent are in equilibrium. Okay, so first option is the correct option. Okay, now also one thing which you should know is, I think you might have heard it also, especially in very cold countries like Antarctica or Switzerland, where there's a lot of cold. So what happens during the winter time? Okay, because of heavy snow. Okay, so everything gets deposited by snow. So the roads are blocked. Everything is blocked due to so much amount of snow. So what people do to melt that snow? Okay, one thing is, you cannot go and just keep on heating all the snow that is present. Okay, and you cannot leave it also, because the snowfall happens for a very long time, for a very long duration of time. So you cannot just wait for the sunrise to come and the snow would melt. So what basically people do over there, they just add salt over these, okay, snow. So if the snowfall is very heavy, the entire city is engulfed in the snow. So basically they do it from helicopter. So they sprinkle salt over the over that particular snow. So we know that when you add a non-volatile solute, okay, the freezing point would depress. So basically the freezing point of water would depress. Suppose the temperature was 0 degrees Celsius. At 0 degrees Celsius it was a ice, okay, or say the temperature was minus 1 degree Celsius. So basically the water was ice at that temperature. Now when you have added salt over it, so we know that freezing point of it would decrease. So suppose the freezing point went to say minus 3 degrees Celsius. So at minus 1 degree Celsius, which was the temperature of the surrounding, the ice would not remain in the solid form. It would melt and it would change into liquid water. Okay, so this is also known as sprinkling of salt over the snow. So if you sprinkle snow, if you sprinkle salt over the snow, okay, the snow or the ice would start melting, because there would be a depression in the freezing point. Similarly, you can also say one more thing, that suppose let us consider an idea of car. So you can see that if we are driving car in the cold condition, okay, now we also know that there is a water inside the car. Okay, so you might have checked that if you raise the bonnet of the car, you will see that there is a water also, and there is one coolant. Okay, now if you see that in those coolant, beside oil, some ethylene glycol is also taken. Now ethylene glycol is a solute. Okay, so it basically what it does, it depresses the freezing point of water. So at places in the countries where the temperature is very less, even in minus temperatures are there, so the freezing point of water has reduced. So at that temperature the water doesn't freeze. So that is the role of ethylene glycol, especially in the radiator. So ethylene glycol are added in the radiator so that the water does not freeze at that particular temperature. So this also uses the concept of depression in freezing point. Okay, so this question can also come in the objective format. This is written in NCERT also. So in cold countries, the radiator is in the radiator some ethylene glycol is added, which depresses the freezing point of water, so that water does not freeze in the cold conditions. Okay, so even if the temperature falls to say minus 15, minus 10 degrees Celsius, the amount of ethylene glycol is added is more, so that depression of freezing point of water is more. Okay, hope this is clear to you. Okay, now let us look at this question. Okay, just read this question. So this was a previous year question, JEE advanced question. So this says that pure water freezes at 273 Kelvin and 1 bar. The addition of 34.5 gram of ethanol to 500 gram of water changes the freezing point of the solution. Use the freezing point depression constant of water as 2 Kelvin kg per mole. The figure shown below represents plots of vapor pressure versus temperature. So some plot has been given to us. Molecular weight of ethanol is 46. Among the following, the option representing change in the freezing point is. Okay, so first let us see that we have added ethanol. Okay, so number of moles of ethanol added would be 34.5 upon 46. Okay, so if we want to calculate the molality, so molality would be 34.5 upon 46 into mass of solvent in kg, which is 0.5. So I think this would come out to be 1.5. Okay, so delta TF in this case would be KF into M. Okay, depression freezing point is always molality into the molar depression constant. So delta TF in this case would become, KF was 2 and this is 1.5. So this would become 3. Okay, delta TF is the depression freezing point. So the initial freezing point was 273. Okay, minus the final freezing point of the solution. This is equal to 3. So final freezing point of the solution would be 270 Kelvin. Okay, so when we have added ethanol, 34.5 gram of ethanol in 500 gram of water, its freezing point would become 270 Kelvin. Okay, so let us understand what is given over here. So some graph has been given to us. Okay, so obviously we can see that, okay, when you are taking only water. Okay, so this was the vapor pressure of this graph. So because we are plotting vapor pressure with temperature, so let us just forget this graph. Okay, we don't need to understand this graph, so just forget this graph. So this is the graph of the pure solvent. Now when you have added ethanol, okay, so when you have added ethanol in water, so the vapor pressure of the solution decreases. Okay, so this is the vapor pressure of the solution. Okay, now this is the graph or the vapor pressure of the solid or the ice. Okay, at this point there is a equilibrium between ice and water. So this is the freezing point. Initially the freezing point was 273. Now this mixture, water and ethanol, and when it is intersecting with ice, so this will be the equilibrium between the water in the water ethanol system and the water solid, that is ice. So the freezing point is 270 Kelvin. So answer would be C in this case. So you can look at these questions, they are not difficult at all, just a very good interpretation is required. So this graph is basically coming from phase diagram of water. So if you don't know the phase diagram of water, the phase diagram of water looks something like this. Okay, so this region represents solid, this region represents liquid, and this region represents gas. So if you can see that this is almost like a straight line. Okay, so this is almost like a straight line and this is a curved. So there is a solid phase over here. Now this line represents equilibrium between solid and liquid. This line represents the equilibrium between, okay, liquid and gas, and this line represents the equilibrium between solid and gas. At a particular point, at this point, okay, all the three solid, liquid and gas lines are intersecting. So at this point all the three phases coexist together. So this is called as the triple point. Okay, so triple point of water is the point where all the three phases, solid, liquid and gas, are coexisting together. Okay, so this temperature is 0.0098 degrees Celsius. So this is the triple point of water. Okay, so this is basic phase diagram of water. Okay, so this is basically a conclusion of Clausius-Clapeyron equation as well. So this is the graph. Okay, so this is basically your solid, this region is liquid and this region is gas. Okay, this line represents the equilibrium between gas and liquid, this region represents the equilibrium between solid and liquid, this region represents the equilibrium between, okay, gas and the solid. So if the pressure is 1 atm, okay, you can see that if the pressure is 1 atm, so we'll say that this is the freezing point. Okay, because at 1 atm the temperature at which the vapor pressure of solid and liquid becomes equal is your freezing point. So when it becomes 1 atm, so this is the freezing point, that is 0 degrees Celsius. Okay, when you extend this line and you meet this graph where the equilibrium between liquid and gas exists, so this is the point where liquid and gas will coexist together. So at this, okay, so basically the boiling point of a liquid is the vapor pressure, is the temperature at which the vapor pressure of the liquid becomes equal to the atmospheric pressure, that is 1 atm. So the vapor pressure corresponding to 1 atm, okay, the temperature corresponding to it would represent as the freezing point, boiling point of water. Okay, so hope you have got this this one, okay, and this is your critical temperature or the critical point, okay. The critical point of water is 374.4, okay. Hope this is clear to you. And beyond this exists supercritical fluid. So we'll do it phase diagram of water, okay, when we do some portion of Olympiad solving. So for the time being, you just need to know about the graph. How does the graph look? What are the regions, okay, where the equilibrium is established, and like how do you locate the freezing point and the melting point and the boiling point, okay. So when the vapor pressure becomes 1, okay, the temperature corresponding to the liquid gas, okay, graph would be the boiling point, and that with solid and liquid would be the freezing point, okay. Okay, so let us look at this question. In the depression of freezing point, it is found that the vapor pressure of the solution is less than that of pure solvent, okay. So we are saying that in the depression of freezing point experiment, it is found that the vapor pressure of the solution is less than that of pure solvent, okay. The vapor pressure of the solution is more than that of pure solvent. Only solute molecules solidify at the freezing point. Only solvent molecules solidify at the freezing point. So this is the correct option, okay, because we know that only solid solvent is formed, okay. So when there is a freezing happening, so we'll say that the liquid and the solid form of the solvent are in equilibrium. So this is incorrect. Now when we have added a solute onto the solvent, so obviously the vapor pressure of the solution would decrease. So we'll say that the vapor pressure of the solution is less than that of pure solvent. So the correct answer is A and D. So this was a previous year IIT question, okay. Even this was the previous year IIT question. So you can see that this is just a basic calculation and the interpretation of the graph. Even if you don't know the graph, you can see that there is a value of 270 and 273. So you will be confused only with A and C graph, okay. But you should know that the region, we have already done this, okay, the vapor pressure variation, okay, of the solution and the solvent. We have drawn graph like this, so this matches with that, okay. Hope this is clear to you. Okay, so benzene and naphthalene form an ideal solution at room temperature. For this process, the true statement is R, okay. Again a previous year JEE advanced question. Again you can see it's a very basic level question. So it is saying that it is forming an ideal solution. So for ideal solution, we know that delta V mixing is 0, okay. Delta G mixing has to be negative, okay. So delta G is positive, this is incorrect, okay. Delta G has to be negative, delta V mixing is 0, delta H mixing is 0, so delta H is 0, delta S system is positive and delta S system surrounding is 0, okay. So now let us understand, okay, the delta S concept, okay. So we know that whenever you are adding a component, okay, in a solvent, so we know that the number of components are increasing and also the volume is increasing, so the enthalpy of so the entropy of the system is also increasing. So we'll say that delta S system is greater than 0, okay. Hope this is clear to you, okay. So we'll say that we also know that delta S system is 2.303 N total R summation of xi ln xi, okay, with a negative sign. So we know that the mole fraction value is ranging between 0 to 1. So log of anything between 0 to 1 is negative. So when negative comes out, it becomes positive. So delta S system is positive, okay. So we know that delta system is positive, delta H is 0. Now what about delta S surrounding, okay. So we know that delta S total has to be greater than 0, okay, because this is a spontaneous process, okay. Now we know that delta G is equals to delta H minus T delta S, okay. Now this is T delta S system and this is delta H system, okay. Okay, so we know that delta G is 0, sorry, delta H is 0, so delta G becomes minus T into delta S, okay. I don't think there is no T term over here, okay. So you can see that because delta S was positive, delta S system was positive, so delta G has to be negative, okay. Now what about delta S surrounding? Okay, now we know that because there is no heat exchange between system and surrounding, delta H was 0. Okay, so there is no heat exchange between system and surrounding, so surrounding would be at the same temperature, so surrounding would not gain any amount of heat, so there would not be any change in the enthalpy of the the entropy of the surrounding. So delta S surrounding has to be equal to 0. Okay, so you can look at this question. This is very basic and logical question. Okay, so IIT picks up such kind of question where they check your ability to analyze a case or the theory which you know. Okay, so a very important point that you should know that whenever a system is ideal, whenever liquid solution is ideal, so we know that delta H is 0, delta V mixing is 0, delta G is negative, okay, and delta S total is always greater than 0, is positive. Okay, now for the system this is the formula. So delta S system is obviously positive because you are adding more number of components, the volume is increasing, so the space available for a molecule to move will increase, so delta S system has to be greater than 0. Okay, now because delta H was 0, that means no heat has been exchanged from the surrounding, so there won't be any change in the surrounding. Okay, change in temperature of the surrounding, so the surrounding would be at the same entropy that it was before, so delta S surrounding would be 0. So answer of this would be B, C, D. Okay, hope this is clear to you. Okay, so this is an integer type question. This says that the mole fraction of a solute in a solution is 0.1. Okay, so the mole fraction of the solvent would be 0.9. At 298 Kelvin, the molarity of the solution is equal to molality. Okay, so a statement has been given to us that molarity is equals to molality and the density of the solution is 2 gram per ml. The ratio of the molecular weight of the solute and the solvent is. Okay, so this was again a previous year IIT question. So in the question some data has been given to us. It is said that density is 2 gram per ml. Okay, the mole fraction of solute is 0.1 and we know that molarity is equals to molality. Find us the ratio of the weight of solute and solvent. Okay, so you can just take some time to understand. Just read the question. So you can say that density is 2 gram per ml. It means that 1 ml of the solution is having 2 gram. Okay, so 1 ml of the solution contains 2 gram. Okay, so 1 ml of the solution is weighing 2 grams. Okay, so we know that the total mass of the solution is 2 gram and the volume is 1 ml. Okay, hope this is clear to you. Now molarity we know is number of moles of solute upon volume of solution in liters. Okay, and molality we know is number of moles of solute upon mass of solvent in kg. Okay. Okay, hope this is clear to you. So molarity is number of moles of solute upon volume of solution in liter. So volume of solution in liter is 10 raised to minus 3. Okay, so I can write this as mass of solute. Okay, let the molar mass of the solute be m solute. This will be divided by 10 raised to minus 3. Okay, so this is number of moles of solute is again mass of solute upon molar mass of solute divided by mass of solvent in kg. Okay, so we know that the mass of solvent in gram is 2 into 10 raised to minus 3. The mass of the solution is this. Okay, so let mass of solute be x. Okay, so that of solvent would be 2 into 10 raised to minus 3 minus x. Okay, so I can write this as 2 into 10 raised to minus 3 minus x. Okay, hope this is clear to you. So we are just using that simple fact that is given in the question, that molarity is equals to molality. Okay, so you can see that these two terms will be cancelled out. Okay, so I'm just using this data, that 2 gram per ml, because nothing is given in the solution in the question. So we'll say that 1 ml of the solution is weighing 2 grams. So total mass of the solution is 2 gram. Let us assume that the mass of solute is x. So the mass of solvent would be 2 into 10 raised to minus 3 minus x, because the mass of the total solution is, okay, 2 into 10 raised to minus 3 kg. Okay, so I will say that 2 into 10 raised to minus 3 minus x is equals to 10 raised to minus 3. So x would be 1 into 10 raised to minus 3. Okay, now hope this is clear to you. Okay, hope this is clear to you. So the mass of the solvent is 1 into 10 raised to minus 3 kg, or we can say that mass of solvent is 1 gram. So if mass of solvent is 1 gram, okay, you can say that mass of solute is also 1 gram, because total mass of the solution was 1 gram. So mass of solute and solvent is same. Okay, so now let us use this data. Okay, just divide mole fraction of solute upon mole fraction of solvent. So this would come out to be 1 by 9. Okay, so mole fraction ratio would always be equal to the ratio of their moles. Okay, we can write mole fraction of solute as mass of solute upon, mole fraction of solute as moles of solute upon total moles. Mole fraction of solvent we can write as number of moles of solvent divided by total moles. So the total mole get cancelled out. So ratio of the mole fraction is also the ratio of their moles. So this would be equal to 1 by 9. Now we know that number of moles is mass upon molar mass. So this is mass upon molar mass of solute. This will be mass upon molar mass of solvent. This is equal to 1 by 9. Now we know that mass of both solvent and solute is same in this case, so they will get cancelled out. Okay, so the ratio of molar mass of solvent upon the molar mass of solute would be 1 by 9. Okay, so the ratio is molar mass of solute upon molar mass of solvent would be 9. Okay, so answer of this would be 9. Okay, so you can see that this is actually a very easy question. It does not involve a lot of chemistry also. So it is basic level question. Okay, it is simply understanding of the question. Okay, it is simply like writing the equations, writing the formulas and just solving it. So I will keep on repeating this. IIT is not difficult. Only thing required is the presence of mind and a very sharp solving skills. If you solve a lot of subjective questions, if you write and solve everything, then things become very easy. Okay, so you can look at this again, a very easy question. So from this data of density we understood that the mass of solvent and the mass of solute was same. Okay, because it was given that molarity is equal to molality. So just we divided the mole fractions. So the ratio of mole fraction is also the ratio of their moles. So from the moles we exactly wrote the formula, moles is mass upon molar mass, mass get cancelled out, so you get the ratio as 9. Okay, hope this is clear to you. You can take a snapshot and try it. Okay, so this is again a question, just read it. So this says that there are two liquids A and B and they form a nearly ideal solution over the entire range of composition. At temperature T, equimolar binary solution of liquid A and B has a Weber pressure of 45 torr. Okay, so we have been said that there is a equimolar, that means moles of A and moles of B are same, so their mole fraction would be half. Let us assume that moles of A is X, so moles of B would also be X because they are equimolar. So total moles is 2x, so the mole fraction would be moles of A upon total moles, which is half. So mole fraction of B would be half. Okay, so we say that when we are mixing this, okay, so when we are taking mole fraction of A as half and mole fraction B of half, we are mixing them together, the total pressure developed over the solution is 45 torr. Okay, at the same temperature, a new solution of A and B having mole fraction of XA and XB respectively has a Weber pressure of 22.5 torr. The value of XA by XB in the new solution is, okay, given that the wave pressure of pure liquid A is 20 torr. Okay, so you have to find this. So we knew that initially PT was equal to P naught A XA plus P naught B XB. So first data, okay, this data was given to us to get the value of P naught B. So the total pressure we know is 45. So P naught A was 20 into half plus P naught B into half. So this is 10, this will go over here, so this will become 35. So if you do this, P naught B will come out to be 70. Okay, so P naught B is 70. Okay, so now from this data you have calculated the value of P naught A and P naught B. Okay, hope this is clear to you. Okay, just read this. This is a very simple question. So this says that we had in equimolar solutions of A and B. So the mole fraction of A and B was half. Okay, and the total pressure was 45 torr. So P naught A was given to us. We'll just use the Raoult's law formula. We'll get the value of P naught B. Okay, so I'm just erasing this step now. I hope you have understood this. So we have found that P naught B is equal to 45 torr. Sorry, P naught B was 70 torr. Right? Okay, so the first part question was basically to find out the value of P naught V. Now this says that at the same temperature a new solution of A and B having mole fraction of XA and XB are mixed together, and now the total pressure is 22.5 torr. So let us say that the total pressure at that instant is 45 by 2. Okay, so we'll say that total pressure is equal to P naught A XA plus P naught B XB. So we can write XB at 1 minus XA. So we know that total pressure is 45 by 2. P naught A we know as 20. This is XA. We don't know the value of XA. We need to calculate. P naught B was 70 and this is 1 minus XA. Okay, so we can calculate this as 20 XA plus 70 minus 70 XA. Okay, so this is equal to 22.5. So this would be 50 XA equals to 47.5. Okay, so XA will get as 47.5 by 50. Okay, so XB would become 2.5 upon 50. Okay, hope this is clear to everyone. Okay, hope this is clear to everyone. Now this is a basic level question. So we want to calculate XA by XB. Okay, so when you divide, this becomes 47.5 upon 2.5. Okay, so this just cancel out. 25 into 20 is 500. So this is basically 19. Okay, so this is your answer. So 19 was the answer. So I think this was the question in JEE Advanced 2018, I guess. Okay, so this is the answer. I think this is a question of 2018 or maybe 2019. So you can see that this is nothing. This is actually a very basic level question. Okay, if you have done a very good research on the content, if you have solved Raoult's law, if you have read all the finer details of Raoult's law, you can easily solve this question. Okay, that's why I am saying focus on the topics that are most important for JEE first. Okay, instead of thinking like that I have not completed this chapter, I have a problem in this chapter, I am weak at this chapter, just think about the positive point of your preparation. Everyone out there who is preparing will not have all the chapters done in a very good manner. So they will be having some great topics, they will be having some topics in which they are weak. Even the rank 1, rank 2, rank 3 students are also not 100% sure of all the chapters. So their level of confidence is very high, so that's why they are able to crack those rank. But if you look at the paper, there are some definite questions coming every year from a particular chapter. Solution is one such chapter, and if you look at the solution chapter, most of the things here are driven through concepts. The numerical approach, the concept, the basic level of understanding of the topics, few examples, ideal, non-ideal solution example, their properties. So questions are coming from there only. So what you need to do is you need to have a very researched level of content where you need to address all those concepts. Go through some good book reading, NCRT. If you are doing NCRT, read the NCRT. If you are reading KS Verma, read KS Verma completely. Okay, don't let your reading stop. Okay, because once you stop reading, your brain stops to process data. Okay, the feeding activity is becoming more common to all the students, that student wants to get feeded up by the content, but that is not the case in IIT-JEE preparation. Okay, the data cannot be feeded into your brain. It has to be understood, and the process will become enjoying, the process will become easy when you start reading and when you start feeling the content. Okay, my role as a teacher, my role as a mentor, to make things interesting for you. That's it. I can give you a guideline, I can guide you till the end, I can show you the right path, I can make you go to those books which will actually help you in creating a very beautiful conceptual level in your brain, but things has to be done from your side. So whether it is offline or whether it is online, everything remains the same. Okay, the only difference is you are getting mentored online, but the work which you have to do still has to be done from your side. Okay, reading is a one very important tool. Don't neglect reading. Even if your teachers, even if your institute says that we'll give you the notes, you just read the notes, that's it, and do a lot of problem solving. Don't listen to them. Okay, just see what questions have been asked in IIT. So they are basically checking your fundamental skills. They are not checking whether you know something which is out of syllabus or not. They are just checking if you have read the things properly, if you have prepared your notes properly, and if you have done a very good problem solving. Reading will actually help your mind to become very fast, and it is the only tool where your mind becomes very fast. Else all the other tools, problem solving and all those things, come secondary. First is reading. Reading gives you a lot of concentration. You take out the data from the question very easily and you create a wonderful concept for yourself. Okay, so don't stop reading, keep exploring. That is how the mind works. If you stop your mind, if you just become focused on one thing, if you are just doing only one type of study, that will actually hamper your preparation. Okay, this knowledge of science is very deep. No teacher in the entire world has the complete knowledge. We all are the part of the same system. We have derived some knowledge from this vast sea of knowledge, some portion of it through reading, through like our understanding of the nature or the practical implications of it. So no one is perfect, even I am not perfect, even you might not be perfect. No one on this earth is perfect when it comes to science. Science is one thing which has to be felt, which has to be read, which has to be explored. If you stop the process to just restricting it to a problem solving skill, then science becomes very boring and clearing paper becomes very difficult. ठीक है, पढ़ो, पढ़कर उस चीज़ का मज़ा उठाओ. मज़ा आ गया ना, फिर काम बहुत easy है. मुझे personally I feel this chapter is very easy. I like solving a lot of questions on these chapter because they are very elementary. 4-5 formula और खूब सारे concepts और एक अच्छा reading. I am ready to solve any amount of question. You see, these are the questions of IIT. This was the question of IIT, this was the question of IIT, this is the question of IIT, this is the question of IIT. Okay, even this is the question of IIT. I think this is 2017 or 2019. So you can see these questions are directly coming from like in the paper of the final paper. So you can understand that logic is the key over here. Okay. Okay, so just solve this question. Just read this now. On dissolving 0.5 gram of a non-volatile ionic solute to 39 gram of benzene, its vapor pressure decreases from 650 to 640 mm of Hg. The depression in freezing point of benzene upon addition of the solute is. Okay, so this was the question in JEE Advanced 2019. Okay, so you can see that every year there are 1 or 2 questions coming from this chapter. So we know that the mass of solute over here is 0.5. Okay, let the molar mass be m, so this would be 0.5 upon m. Okay, similarly the mass of benzene in this case is 39 gram, which is the solvent over here. So the moles of solute is 39 upon 78 because it is given the mass of benzene is 78. So this is half or 0.5. Okay, so mole fraction Okay, so mole fraction of solute in this case would become 10.5 by m divided by 0.5 by m plus total moles is 0.5 by m plus 0.5. So this is the mole fraction of solute. Okay, so we found the moles of solute, 0.5 upon molar mass, we assumed it as m. The mole fraction of the solvent is, the moles of the solvent would be mass of solvent benzene upon the molar mass, which is 78. So the moles of benzene is also half. So this is the mole fraction of solute. Now we are saying that when we are dissolving 0.5 gram of non-volatile solute into benzene, the vapor pressure is decreasing from 650 to 640. So this is a case of relative lowering in vapor pressure, and this is a non-ionic electrolyte, so we don't have to take care of the Van 't Hoff factor. So this would be P naught minus P upon P naught equal to mole fraction of solute. Okay, so P naught over here is 650, P is 640, this is 650, this is equal to 0.5 by m divided by 0.5 by m plus 0.5. Okay, so this you can see that this is 10 by 65. Okay, so you can write 10 by 650, so you can cancel this, so this will become 0.5 by m plus 0.5 equals to 65 into 0.5 by m. You can cancel out this 0.5, 0.5. Okay, so this would be 1 by m plus 1 equals to 65 by m. Okay, so I can write this as 64 by m equals to 1. I will just take this 1 by m to there. So this will become 64 by m equals to 1. So m will become equal to 64. Okay, so the mass of the molar mass of the solute is 64. So this data was given to get the molar mass of the solute. Okay, so the molar mass of the solute, which we assumed as m, is 64. Now we need to find the delta TF, which is equal to Kf into m. Okay, so the value of Kf is 5.12. The molality of the solution would be, okay, moles of the solute, which is 0.5 upon 64 into mass of solvent in kg. So the mass of solvent would be 39 into 10 raised to minus 3. Okay, so let me check if I can do the calculation directly. So this goes above. So this becomes 0.5 into 2 into 5.12 would be 2.56. 2.56 into 10 raised to power 3 would be 2560 divided by 64 into 39. Okay, now this is very easy to solve. So this is 40. Okay, so this is basically 40 by 39. So this would be 1.02. Okay, so this is the answer. So this is the question. I think this was last year 2019. Very straightforward question. Okay. Now look at the steps I am doing. How I am solving it so quickly. How I am like solving the data so quickly. You need to understand this. Okay. I was very weak in my 12th class. I was not like this. Okay. I grew thinking, reading, and the concept becomes so clear that I was able to do things with a lot of confidence. So the trick here is to solve subjective questions. If you solve a lot of subjective questions, the pattern becomes very easy. Okay, so this is it. Okay, I hope you have understood this question now. Okay, so let us look at one more question. This says that Mx2 dissociates into M2 plus and X negative ion in an aqueous solution with a degree of dissociation of 0.5. Okay, so we are saying that Mx2 is dissociating into M2 plus 2X negative. So let the number of moles of this be N. So alpha is the degree of dissociation, so this would be N minus N alpha. 1 mole of this is giving 1 mole of M2 plus, so N alpha would give N alpha amount of M2 plus. 1 mole of this is giving 2 mole of X negative, so N alpha would give us 2 moles of N alpha. So total moles finally would be N minus N alpha plus N alpha plus 2N alpha. So you can see this will get cancelled out, so this will become N 1 plus 2 alpha. The value of alpha is 0.5. So if you put 0.5, so this will become 2N. So Van 't Hoff factor would be 2N, total number of particles finally, upon initial, which is 2. Okay. So this says that the ratio of the observed depression freezing point to the value in the absence of ionic. Okay. So you have to find this delta TF observed or the experimental one divided by delta TF normal. Okay, so this we know that this is equal to delta TF observed is IKF into M. Okay, the one done through experimentally has to incorporate the Van 't Hoff factor. Okay, theoretically we are expecting it to be KF. So we know that the ratio of Van 't Hoff factor is delta TF observed upon delta TF normal. Okay, so the answer would be 2 in this case. Okay, because the Van 't Hoff factor is 2. So again, this is a previous year JEE advanced question. Like, ask yourself, are these questions difficult? If you are facing difficulty in such questions, it means that you have missed out on some of the skill level that has to be incorporated in your preparation. Okay, start from the very basics, start from the NCERT, have the very, like, even though it might appear very silly to you or to your friends or to anyone like from where you are getting mentored, but the most important thing is to start from the scratch, build the basic concept, do a subjective level problem, keep on improving the levels, keep on improving the difficulty of the question, and at one time, if you have done the coverage of the theory well and you have mastered the concepts well, then you will definitely get all the questions done very easily in JEE Advanced. Solution is a very important chapter. Last 4 to 5 years, every year there is a question on solution. It has also come twice in 1 year. So you can see the chapter is very impactful. Okay, hope I have been able to do justice. Okay, so this is the first time that I am teaching online, so there might have been some like mistake in writing or might have committed some writing errors over here. So please neglect those, because I hope you can also understand that this is the first time facing a camera and delivering a lecture to you, but things are much more. The concepts that I can give to you is much more than what we are getting learned right now. So this is the start. So as the time will progress, we will also launch a Olympiad program after some time when we have covered a good amount of syllabus, where we will be focusing on solving of National Chemistry Olympiad papers as well as the INCHO paper. So all the things that you are doing offline will be there done online by us. So you don't have to worry about the level of the content, the difficulty level of the content, the quality of the question papers. We have been there for almost 15 years now. We have trained some very sharp mind of the country. We have even brought results from very average students who were very struggling in their preparation. So we'll get all the experience, all the best expert guidance from the best mentors of the India. Okay, I hope you enjoyed the session today. Okay, so just go through it once. We have completed the solution chapter now completely. You can just go through the notes. You can read your NCERT line by line, marking with a pencil, and then you can do problem solving from the daily practice problem sheet or from the books that you might have purchased for your preparation, or from the content of your institute where you have been learning all this while on a offline mode. Okay, so I would love to hear from you. So if you have any feedback, if you want to get in touch with us, you can call on our number and you can get in touch. Okay, so write a feedback about us. I would like to hear from you. So in case of any problem, I would like to get in touch with you so that we are able to rectify the mistakes. Okay, so this is it for today. So tomorrow we are going to start with a very important chapter of electrochemistry. Now electrochemistry is also a very important chapter. Every year one question is coming on electrochemistry. Kinetics, solution, electrochemistry. 3 questions for sure it is going to come in JEE Advanced. Okay, so hope you like the lecture. We'll catch tomorrow for an interesting session on electrochemistry.